Okay, welcome everybody. My name is Ricardo Vinuesa. I'm an associate professor at KTH in Stockholm, and today I'm going to tell you a bit more about what we discussed in the previous videos on explainable deep learning to try to identify coherent structures in turbulence. So if you remember the previous videos, we were using this explainable deep learning method to try to see how we can identify regions of importance, and today the focus is going to be more on experiments. So we're going to take the results that we applied for the numerical implementation, and we're going to see if they hold in an experimental realization of the flow, and we'll try to interpret things a bit more. This is research funded by the European Research Council, the ERC. Now, if you remember, and we will also post the video in the description, the previous video, so you can see all the context of this explainable deep learning framework. But the idea is that we're using the SHAP method. So in a first step, we have the current state of the flow, and those are three-dimensional fields of U, V, and W fluctuations, and we're going to predict a future state of the flow, so the three fields of U, V, and W, through a 3D U-net, so basically a deep neural network based on convolutions that can exploit the spatial patterns in the data. That's the first step. Once we have the future prediction of the flow, and remember that this is for characteristic times of the near-world region, in the second step, we're going to identify features in my input. So basically, in my initial flow fields, we're going to look for regions of intense Reynolds shear stress. These are going to be the Q structures. And that's going to allow us to segment the flow. So essentially, we're going to have three-dimensional volumes of intense Reynolds shear stress, and these volumes will constitute the segmentation of my input. The third step, we're going to be using basically a game theoretic approach called, the SHAP algorithm. It's based on Shapley explanations to really try to interpret a little bit more, give explanations into the importance of the different features of my input. So long story short, what I do, as you can see here at the bottom, is that I have my structures of my input. Then what I do is that I will remove structures from my input, and as I remove them, I will perform the predictions again. Now, the idea is that each of these structures from my input will have different impacts on the error. Some of them will reduce or increase the error in different amounts, and we want to really see the structures which, if they're not in the input, they impact the most the error of our neural network. Once again, if you want to see more details, please check the previous video where we explain the kind of like the methodology in more depth. Just remember that the SHAP framework allows us to go from removal of inputs, from really identifying those three-dimensional volumes and assessing their impact on the error, to a ranking of importance. And that's the SHAP value. The SHAP value is basically that ranking of importance from each of the structures in our flow. Remember also that this is work led by Andrés Cremades. There is a paper in archive, so you can see all the information and all the details there. Good. So I want to, before going into the application to experiments, I want to highlight two main assumptions that we have in this method. In particular, this is what we call the kernel SHAP implementation. This is a particular implementation of this SHAP algorithm. And we have two main assumptions. The first one is the fact that the model G, and remember the model G from previous videos, is a model representing the error between the neural network and the DNS. So basically between the model, the surrogate model, and the truth, the DNS or the experiment, whatever you consider the truth, that model G is linear. What does that mean? That means that to model the error between the neural network and the ground truth, we are using basically a linear superposition of all the structures in our flow. Now, of course, we have a highly chaotic turbulent channel, and we're trying to represent that error in a linear function. Well, the point is that the difference, f minus g squared, so basically the difference between the true error, between the neural network and the truth, and the linear model for that error between the neural network and the truth is on the order of 10 to the minus 7. and the quantities we're trying to predict is on the order of 1. So even if we're using a linear model for that error, and we have a chaotic nonlinear system, we have so many extractors on the order of 200 per field and several thousands of fields that the linear leading order approximation to that error is sufficient, and we could go to higher order interactions among extractors and quadratic terms and so on, but that's not needed. The linear representation of the contributions of those extractors to the error is enough by judging by the level of accuracy with respect to the true error between the neural network and the ground truth. Second, we are taking the extractors one by one. This is again the schematic that I showed before. And of course, we have once again a chaotic, nonlinear, complex turbulent channel. Is that representative of the physics, of the complex interactions present there? Well, in reality, when we take away these extractors, we do it in the form of coalitions. And a coalition is a group of extractors, from 5 to 10 typically. So we take one extractor, and then it's within a coalition. We remove it and apply the predictions and see its contribution to the error. The same extractor is now found in another coalition with another set of extractors, and we repeat the same game. We do that for different numbers of coalitions in such a way that we can assess the role of that initial extractor in many different environments, in many different contexts. So with larger scales, with smaller scales, with different interscale interactions. So in such a way, we can, in an effective manner, represent the multi-scale and inter-extractor transfers present in the turbulent channel. And the way that this is done, we have really looked thoroughly at hyperparameters such as the number of coalitions, the size of those coalitions, and the results are robust and converged. So in principle, we are able, with this coalition-based method, to really reconstruct and in a way approximate quite efficiently the inter-extractor interactions in the flow. Now, having clarified these 2 points, we are convinced that our method is representative of the physics of the flow, at least within the surrogate accuracy that we have created. And we're going to try to see how we compare the results from the numerics that we showed last time with the results that we're going to provide now based on the experiment. For experimental work, we teamed up with Ivan Marusik's group, that's in the University of Melbourne, for one very important reason. Now, let's assume that I do my DNS, and then I identify my 3D extractors, very nicely resolved, and I really select the most important ones, and that's what I need to be able to control to really have a big impact on the turbulent flow. Now, a low Reynolds number DNS might not be exhibiting the same important extractors as a very high Reynolds number experiment, because the physics changes, right? So there's going to be a difference in Reynolds number when it comes to what is more important. That's the first thing. Second thing, even if I could do a DNS at the same Reynolds number as the experiment, in the DNS I'm identifying 3-dimensional, nicely, finely resolved structures, and in the experiment, if I'm lucky, I will be able to get a 2D plane, a 2D PIV plane, maybe a small region with some 3D tomographic PIV, but the usual thing is that I will have 2D planes with low resolution. So even if I could find super nicely resolved extractors in the DNS, which are most important, I don't have a chance of finding the same extractors in the experiment. So the question now becomes, from whatever I can measure, what is the most important stuff? What are the most important features in my flow among those that I can measure? And that's why we want to apply this method directly to the experiment and develop a surrogate model on the experimental data that we have. Now, going back to the group in Melbourne, we looked at this very nice setup that they have here. This is a towing tank, which you can see also the schematic down here. In the towing tank experiment, what people do is that you would take this plate and then start its motion suddenly in such a way that the boundary layer will grow in time. Okay, so instead of developing spatially, the boundary layer develops in time. This is a quite convenient way to achieve high-resolution snapshots, which we will be using for our comparisons with the DNS. They perform PIV measurements, around 6,000 snapshots, so very similar to the type of data set that we have in the DNS. They obtain 2-dimensional fields of U and V, so those are the stringwise and volumetric fluctuations. The viscous time is a bit more than 1 viscous unit. The friction Reynolds number is an order of magnitude larger than that of the DNS, which is pretty good. And we perform the percolation analysis in 2D, because now we're not going to be looking at 3D elements of a strong Reynolds shear stress. We're going to be looking at 2D elements, but the percolation analysis will be done in the same way by optimizing H, so that's the hyperbolic hole threshold, in order to maximize the number of 2D structures in our domain, basically. So this is what we have here, and let's look at some results. Over here, we're showing you, first of all, the SHAP value in the vertical axis as a function of the surface of the structures. Remember that now, instead of having volumes, we will have surface. And then these are going to be scale linear units. In this part over here, we are showing you by colors the type of structures that we are finding with respect to the quadrant analysis. Okay, and of course these are joint PDFs. So these joint PDFs are going to represent the joint probability distribution function of the importance and the size of the structure, basically. So over here, what we have is a good correlation between the importance score and the SHAP value and the size of the structure, which is exactly the result that we found also in the DNS. Interestingly, here, of course, the ejections, which are in brown, are still the most important ones, but in blue, we find the sweeps. The relative importance of the sweeps becomes more prominent, and that's well known from the turbulence literature as the Reynolds number increases. So that's no surprise, this is corroborating a known result from the literature. In this panel over here, what I'm showing you now is the SHAP value per unit of surface as a function of the surface of the structures. And again, these results are in agreement with the DNS. So we have this region over here with the largest structures, which are not the most important. The most important are now here, the most important per unit of surface. And those are medium-sized ejections, mostly, with some sweeps and some inward interactions. So once again, the relative importance of the sweeps becomes magnified because of the Reynolds number, but other than that, the trends are in very good agreement with those of the DNS. Now, if we look at the Reynolds shear stress, remember that we are looking at now two-dimensional regions of a strong Reynolds shear stress. The good correlation between the SHAP value and the Reynolds shear stress of the structures is still there. Once again, this is in principle not surprising because we are looking at regions of a strong Reynolds shear stress. So it kind of makes sense that the elements with the highest contribution to the error are the ones with the highest Reynolds shear stress. Once again, the importance of the sweeps over there is increased. The most important result is now in this panel over here, because when we represent the SHAP value per unit surface as a function of the Reynolds shear stress per unit surface, now we have three different regions. In region A, the first thing that we have is a big spread of importance values for the same Reynolds shear stress. So that correlation is completely gone. In region B, which would be this region over here, we have the structures with the highest Reynolds shear stress, and those are not the most important ones. The most important ones would be the ones in region C over here. Look, these structures over here have very low Reynolds shear stress, and they have the highest importance per unit surface. This really confirms again that the intuitive conclusion that the Reynolds shear stress should be the most important is not necessarily true, and we need a more objective definition of importance, such as the one that we provide now with our data-driven method. Now, what we have done so far in the previous video and in this one was to first use kind of like a preconceived criterion. We assume that the Reynolds shear stress is important, and then we identify regions of a strong Reynolds shear stress, and among those, then we apply the explainability, and we try to see from those Reynolds shear stresses which are more or less important. That's interesting, but that's not exactly what we would like to do. What we would like to do is to use this method to identify completely new structures regardless of the initial assumptions. So I want to be completely independent of what I have in the past, over the past decades, thought was important, the Reynolds shear stress, the vorticity, vortex clusters, lambda 2. I want to define new structures purely and objectively based on importance. Now, good news is that we have done that in the experimental dataset in 2D. So what we did was to, first of all, use a new implementation of the SHAP. This is the so-called gradient SHAP developed by the same group that developed the kernel SHAP. The idea is that this method is more computationally efficient, and that allows us to calculate the gradient SHAP on each grid point of the instantaneous flow fields. This is what you can see here at the bottom. So instead of taking the assumption of a strong rain or shear stress and take those elements and apply the shape there, I apply the shape value for each of the grid points of our domain independently. And then what I want to do is look at the regions of highest importance. We can do that as follows. The gradient shape also computes an importance score for the U and V separately. So we don't get a full shape as we had before. Now we have an independent value of the shape score for each of the channels separately. This allows us to compute, first of all, over here, some sort of norm of the shape by taking into account the shape of the U and V components. And over here, I'm looking at the local RMS of the shape in each of the regions of the domain. This will depend, because this is a boundary layer, on X and Y. So I'll take the norm of the local shape value, the norm of the RMS of the shape value, and I have again this H, which is this hyperbolic Hall threshold, which through percolation analysis I can also maximize. And then I will be able to obtain the maximum number of extractors for this particular threshold that I'm defining, again, purely based on importance. In this figure below that you can see, in white, I'm showing you the Q events, so the instantaneous extractors that come from the rain or shear stress assumption. And in this kind of pink color, what I'm showing you is the extractors based on the shape, based on the importance, completely objectively defined through importance. The key is that I have a 70% overlap between the Q events and the shape extractors. What does that mean? Well, this is in principle a good result, a satisfying result, because the fact that the Q events are quite important, that 70% shows that, is reassuring. The rain or shear stress are regions of strong fluctuations, so obviously they need to be important for the predictions, but they do not tell the whole story. The whole story is told through this objective way of importance, which is the shape. And that discrepancy of 30% is precisely what will come in with more in-depth physical analysis to completely understand the role of these more important extractors. And the goal is to use them for flow control. So once we know what are the most important extractors in the flow, and we can define them objectively, we can, through deep reinforcement learning, and we have many videos about that in the channel as well, devise completely new flow control strategies which are targeting the inhibition of the presence of these shape-based extractors in the flow. And then when those are inhibited, we're really having a big impact on the turbulence mechanisms, hopefully leading to physics-driven, very efficient flow control strategies. I want to also highlight that we always have, as in all the videos, our repository, so feel free to go there to check all the databases that we have in our group, and feel free to reach out if there are any questions. And that's all I had for today. I want to thank everybody who made this possible, including InfraVis, the KTH Visualization Studio, once again the ERC for funding the research, and feel free to reach out also. There are more videos in the channel. Through social media, you can also talk and discuss if you have questions or ideas, and I will see you next time in the next video. Bye.